Hi everyone, this is the seventh and final video of our WAVES unit this year, and it is on conservation of energy. Your essential question is how and why does energy move around in systems? So in our previous video, we talked about lots of different types of energies. And the truth is that energies don't just stay as one type in one object for very long. In fact, energy can be transferred from one object to another and has been getting transferred all the way back to the Big Bang. So we can track the energy that we have in the world around us all the way back to the beginning of the universe, just like we can do with mass and all the mass that we have around us. So let's look at an example. So if you have a light on in your room, okay, the energy that's being produced from that lamp is light energy. And that light energy does not originate in that lamp. It comes from somewhere else. So it's coming from the electrical energy that's running through the cord to the lamp and into the socket where it's plugged into the wall in your room. Well, that electrical energy actually doesn't start in the wall either. It goes all the way out over the power lines to, in the Pacific Northwest, we use dams to generate our electrical energy. So it goes to the dam, and there it's going back to the motion of the turbines spinning in the dam. That electricity is coming from the motion of those turbines. The turbines are spun because you've got water stored up behind a dam, and that water has gravitational potential energy in it. That water ended up behind the dam because the moisture in our atmosphere, that water had been warm and up high in the sky in order, like in the water cycle. So we have moisture up high in the sky, and it was able to evaporate and go up there because of sunlight warming it up. So we have light energy that's transforming into thermal energy. Where did that light energy come from? Well, it came from nuclear energy in the sun's core. So in the center of the sun, you have nuclear fusion going on. And then before that, we talked about last week how the sun and stars, they're made up of gases, right? So originally hydrogen and helium that have been pulled together because of gravitational energy a long time ago. And that brings us all the way back to the Big Bang. So all that hydrogen and helium and space gas was created from the Big Bang. So we can track all these different types through different objects all the way back to the beginning of the universe. So not only can energy be transferred from one object to another object, like in our last example, but it can also be transformed into different types. And that can go from within a single object, or it can be transformed across a system of objects. So let's take our skydivers as an example. So these two people have jumped out of an airplane high up above the surface of the earth. So they started out with gravitational energy. They had some distance that they had the potential to fall. And as they step out of the plane, that gravitational energy is transformed into motion energy. Here's another example with a little girl inside one of these big inflatable round spheres, right? And she has chemical energy stored in her body from food that she's eaten. And she is transforming that chemical energy into rotational energy as she pushes on the sides of the ball and it starts to rotate and move. So often during energy transformations, there are other types of energies that are generated. And we call these waste. So there's a little bit of waste energy generated as well. Some common waste energies could be wave energy, which is essentially sound, like sound waves, and heat from friction, so thermal energies. So when I, let's say, clap my hands, I'm transforming motion energy into wave energy by making that clapping sound. And maybe some of the waste as well is the heat, because a byproduct of that clapping is that my hands get warmer. So through these energy transfers and transformations, we can see how systems, the types of energy in systems, can change over time. And we can actually track this. So we're going to look at an example here. We've got two kids going up a hill. Then they get to the top of a hill, and then they fall down the hill. Okay, so what kinds of energies do we have in this system over these 3 time intervals? So if we look at the first picture, before they start to go up the hill, these children have chemical energy in their bodies. We're just going to estimate it at 10,000 joules. So they start with chemical energy before they head on up the hill. They get to the top of the hill, and since they are above some sort of point, they have some distance that they could potentially fall. We say that they have gravitational energy now. Now, on their way up the hill, okay, their chemical energy went down. We don't have it in our diagram anymore, but some energy was given off as waste. So this could be wave. Maybe they made noise as they were going up the hill, and their bodies gave off heat. Maybe they got hot and they gave off heat as they were going up the hill. So our system at this point has gravitational and some waste in the form of wave and thermal. In our last kind of snapshot in time of our system, now the children are falling down the hill. So that gravitational energy is being transformed into motion as they start to fall. And they're also losing some energy in the form of waste, or some of that energy is transforming into waste energy. So wave, they're probably making a lot of noise now, and thermal. As they bump into the ground and tumble, there's friction between them and the ground. So a lot of that energy is being transformed into thermal energy. So question for you, what kind of system is this? And is energy conserved? So I want you to take a minute and look at the system. So we've got before kind of step 2 and step 3. Okay, so looking at the numbers you see at the bottom of each box, what kind of system can we tell that this is? And is energy conserved in this system? So take 20 seconds or so to think about what kind of system is this. And remember, your systems are open system or closed system. So what I notice here, if I'm trying to figure out what kind of system it is that the total amount of energy in our first box adds up to the total amount of energy that I've listed the second box, and the same for the total energy in the third box. So these are 3 snapshots in time. Each have the same sigma energy or total energy in them. So I would call this a closed system. We haven't lost any waste energy or any energies outside of our system. Is energy conserved? Well, conservation means to keep something the same, to try and keep something the same. And so by this picture, since sigma E is staying the same in each time interval of our system, yes, energy is definitely conserved in this closed system. A handy way that we can visualize how this energy changes from type to type is through using energy bar charts. So if we look at our system from before with our 3 phases in time, what we can do is we can make a bar graph showing the types of energy that are involved in the system, how much they are, and including the sigma E, or the total energy. So before they start to climb, we said they mainly had chemical energy. So you can see the bar down here on the left. And then we always want to have a sigma E bar representing the total. So since there's only one type in this system currently, the sigma E bar must be the same height as the bar that represents chemical energy. This is going to change for a time period too. So when the students get to the top of the hill, you'll notice that they've used up all of their chemical energy, but it hasn't gone away. It's just transformed into two different types. And in this case, we have a gravitational energy bar and a waste energy bar, which is including your wave and thermal. One thing to notice here is that your sigma E, since we said this was a closed system, the sigma E has to be the same as it was in the first graph. So the gravitational energy plus the waste energy bar is going to add up to the height of the sigma E bar. So the blue plus the yellow equals the total gray. In our last example, this is where the children are tumbling down the hill. So you'll notice that the blue bar, which represents that gravitational energy, has gone down because they are not as high up as they used to be. They are closer to the bottom of the hill, so they have less potential to fall. That bar has shrunk. The waste energy has gone up because they have got friction with the ground. They're making a bunch of noise, so sound wave energy. And we have a new bar there, which is motion. So as they're rolling, some of that energy is being transformed into motion. But you'll notice at the end that the sigma E is the same as it was at the top of the hill, and it was the same as it was at the beginning before they started to climb. Again, indicating a closed system where all the energy is being conserved. It's time to revisit our essential question and write a short summary. So how and why does energy move around in systems? To write the summary, you could even think of an example in your life. Maybe you play a sport or a musical instrument. And I'd like you to think about how is energy transferred and transformed in that activity that you like to do. So you can write your summary in that sort of framework. And here is a Calvin and Hobbes cartoon.